For dynamic programming, when we learn that Fibonacci numbers, I give you a brief introduction about dynamic programming. Yeah, but in this one, in this part A of lecture 12, we will see more examples. We try to get a better understanding on this new problem-solving idea. So very important, very useful, but usually pretty challenging. Yeah, not that easy. So you need to have some experience. Yeah. The first question for this part. All right. Yeah. Change making problem. So let me give you the problem first. Yeah. Making changes. Yeah. Many different ways. All right. There are m denominations for the coin, D1, D2 through Dn, with D1 equals 1. So then D1 less than D2, strictly. So we arrange these denominations in increasing order, making D1 equals 1. That makes sure we always have solution, because you can use 1 cent to make any change number. You get solution. Yeah. All right, but we want to find the best solution, not just the one solution. We know there is a solution, but we want to find the solution with the minimum number of coins. All right. In order to make change for amount n cents, we need to get total number n cents using these m denominations. You have many different ways. Okay? Yeah. Find the minimum number of coins. Yeah. Among all those ways, the minimum number of coins. There must be such optimal solution. Yeah. Because you only have finite number of solutions. Definitely you can find one with minimum number of coins. Assume that you can use unlimited quantities of coins of the n denominations. You can use 7 D1, 5 D2, unlimited number of coins. But make sure the minimum number of coins. Yeah, that's the optimality criteria. Yeah. All right, so let's look at this optimization problem. Yeah. Usually for an optimization problem, there are two basic methods people can use. One, greedy algorithm, another dynamic programming. Yeah. For our computer science algorithm problems. Typically, these two methods can be used. Yeah. So that's why our lecture 12, we talk about these two closely related topics. Yeah. Greedy algorithm actually much easier than dynamic programming. Greedy algorithm, yeah, because when we make a decision, we try to make it the best local view decision. Local view. I emphasize this local view because it is very hard to make global view. How can you get a global view? People usually are not very good at making good predictions. So if you cannot make good predictions, you can only make your decision based on the current a few steps. So that's the greedy algorithm. Yeah. All right. Yeah, because greedy algorithm is the main topic of our part B. So here I do not talk too much about the greedy algorithm. Yeah. But we know it is relatively easy. But the greedy algorithm has some problem, has some, big drawback. It cannot guarantee it works. Sometimes it does not work. Sometimes it does not work. So you have to use a different way to solve. Here, first we look at a simple example. Try to get some sense of this problem. Suppose we have denominations like this: 1, 2, 5, 7. These 4 denominations for the coins we can use. Now n equals 10. We want to, how to choose the coins to get this 10 cents. But you need to have the minimum number of coins. Okay, so we can try different ways. 7 plus 2 plus 1, that's one way. You need 3 coins. 1, 2, 3, 3 coins. But this may not be the best solution because you can use 2 5 coins. Only two coins. This should be the best solution because nobody can get a 1 coin solution, right? You don't have 10 cents here in your given denominations, so there is no 1 coin solution. Then the 2 coin solution should be the best. So we can take it, the solution. All right. But we want to find the general solution. This is a special question. So we want to get a general solution. So how to get that? First, problem representation. We want to represent it in math formulas. All right, so how to represent it? So for the denominations, that's the representation. Then we need to determine how to choose the coins. Okay, so here, and representation should be D1. How many D1s we want to choose? Here we use a variable A1. D2, how many D2 we should choose? D2 coins. We use A2 and so on. DM, AM. Then we can write this expression. For the AI, the condition is AI greater or equal to 0. We allow it to be 0. So we do not choose the denomination, the coins with that denomination. Okay? All right. So our formula is this. N equals A1 times D1 plus A2 times D2 all the way to AM times DM. So that's the, constraint. So we call this is the constraint. Okay? So the coin combination you choose, you have to satisfy this equation first. Then our minimization function we need. The number of coins, we use S sub n equals the total number of coins you use, A1 plus A2 plus AN, ... Okay? We want to find the minimum number of this function. Okay? So that's the mathematical representation of the problem. Okay? The question is how to solve this problem. Okay? All right, our first try. The first try, at the beginning, we do not have much experience, so we want to try a little bit. The first try, usually people use the brute force method. Okay? People tend to use the brute force method. But here you can see even if you try the brute force method, any possible way. Very hard to describe the number of A1, A2, all these numbers. How do we, it's so hard. Yeah. So it is not easy. Even the brute force method, it is not easy. Yeah. All right. Here, the reason it is not easy is it is hard to organize data. For the data we have, how to organize the data in a nice way so we can, we can process the data. Yeah. So this is the main problem we have. How to organize the data. We need to find a good way to organize our data. Yeah. All right. So now the new idea. Use recursion to help us organize the data. Recursion. Yeah. Here you can see the recursion idea is so important for this class. Here we need to use it again. Recursion, so we basically, change the problem size and then look at the relationship between two problems with an adjacent problem size. This recursion, yeah. So we use the size reduction method idea. Size reduction. We need to reduce the problem size a little bit. Then compare with the original problem. Can we increase the problem size from the lowest gradually to the size given in the original problem? That is the basic idea. Okay, all right. Let's find the recurrence relation, but we need to do some analysis here. Usually this is the most important step. After you get this recurrence relation, then the remaining implementation part much easier. Yeah. Let's work on this hardest part. First, we need to define subproblems. For dynamic programming, one important step, you need to define appropriate subproblems. That's so important. Okay. Here, let me define the subproblem. Define S sub k as the minimum number of coins for a change with value k. Okay. So the value n, original problem value n, we can change that. We can reduce that n number to k number. Then we assume we have another optimal solution for it. Then we look at the relationship. Sk, Sn, what is the relationship between these two subproblems? Yeah. All right. Problem split. For problem size reduction, we need to split the problem size. Problem split. How to split a problem. Yeah. Here I want to introduce a commonly used method. The easiest method, commonly used method. It is called single piece reduction. You reduce the problem size by what? By single piece. So what is single piece? Because for your particular problem, you may have that piece definition. Here our piece definition is the coin. Okay? Coin of certain denomination. A coin is a piece in our particular problem. But when you go to different problems, then you need to define the meaning of different pieces. Yeah. So here, single piece reduction. Yeah. All right. Or single coin reduction. We can interpret in this way in our current problem. All right. So one coin, yeah, that's the interpretation of that piece. Okay. So one coin means one piece. Yeah. All right. Here, I want to do some work. My analysis work, I put it in this small area. Problem size reduction work. Yeah. So let me, work a little bit. Yeah. Our original problem, S sub n. Yeah. Now let's do single piece reduction. How to do a single piece reduction? One piece means one coin. Okay? Reduction, one coin. That means you take away one coin. Okay? Yeah. So suppose your goal is n cents. Yeah. Here you reduce that goal, not n cents, and minus one coin. That you set another goal. Okay? You set a goal before your final goal, right? That intermediate goal. N cents minus one coin. That's the single piece reduction. N minus one coin. Okay? All right. Yeah. All right. Yeah. Not working. Oh, no. Yeah, I may need to change the battery. Yeah. Let me try a few times. If it's not good, I need to change the battery. All right. Take away one coin. But one coin, you have D1, D2, DM. Which one you want to take? Right? You need to make that decision. Which one is the best? You don't know. So that here we use the general DI. Because we don't know, this DI can be any coin. Can be a coin with any denomination. Okay? Yeah. General. Yeah. But after you take one coin, what is the problem size? You reduce the number of cents. For your goal, what is that number? That number is n minus di. Because you take away one coin, the face value of all the coins is reduced by di. Okay, so this is your new problem size. Okay, so what is the optimal solution for this new problem size? Using our notation, using our general definition of the subproblem, that is S sub n minus di. Okay? Yeah. So we have that expression. This is the best solution. The number of coins we have. Okay? Now we want to compare the difference. What is the difference between these two numbers? Sn and S sub n minus di. What is the difference between these two expressions? Now, we know Sn, that's the number of coins for the minimum optimal solution. Number of coins for the optimal solution for this face value. Okay? But if you look at our coin reduction, single piece reduction, we reduce the coin number by one. Single piece, one coin. That means the coin difference is 1. Okay? The coin difference between these two numbers is that 1. Okay? So now, based on this analysis, we are ready to write out recurrence relation. Okay? So this is the recurrence relation. Sn equals the minimum number. Yep. Optimal solution, we want to find minimum number. Because that I could be any number from 1 through n. Okay? Any number from 1 through n. So when we do reduction, we try all the possibilities. We reduce the problem size by the first coin, coin of first denomination, coin of second denomination. We try n times. And we pick the one with the minimum S number. Then look at that difference, because that single coin reduction, one coin difference. So we need that one back. We add that one back. So we get this final recursion formula. With that formula, can you solve the problem? We have the recurrence relation. Now you need to write a program to solve it. I think now it is much easier, right? Given recurrence relation, write a program to solve it. It should be much easier, right? Much easier than you find this recurrence formula, right? So that's why this is the key step. Recurrence relation key step. The second step, write a program to find a solution. Okay, yeah. All right, so here, now I want to go to the second part, find a solution. Although here I do not need to write a program, but let me give you step-by-step details solving this problem based on the recurrence relation we just derived. All right, the topic is how to organize data. Now we have enough information to organize data. Okay, so we have the recurrence relation. Then we need another component to help us organize the data. So here for the dynamic programming, we need another important component. One component, important recurrence relation. This is one component, the first key component. The second component, you need some way to organize data. You need some data structure to help you organize the data. That's the second component. Yeah. Let's see. The essence of dynamic programming, those two key components, the essence. Okay. Use a table. Yeah, this is data structure, table, or dictionary. Sometimes people also call dictionary. Table or dictionary, the same meaning. Okay. And recurrence relation. Yeah, that one. Okay. Two component. Okay. Component one, component two. Okay. To organize data. That's the essence of the dynamic programming. Okay. Yeah. Here, because when I talk about the meaning, the essence, these two important components, let me explain this, the meaning of this programming. What's the meaning of programming here? Okay? It is not the meaning of you write a program, coding, you write it all, high-level language code. It's not that. Programming, you write your code. Coding, it's not different meaning. This programming, the meaning here is very old time, the original meaning from the old time, many, many years ago. Okay? Yeah. Even, long time ago, hundreds of years ago. Okay? Programming means using table to organize your data. Okay? Put your data arrange your data in a table. Okay? Tabular. Okay? Tabular. Okay? Using the tabular way to organize your data. That way people call it programming. Okay? Yeah. So why is that? Yeah. That's the old time story. Okay? So at that time, no computer, so no coding, no high level language, but people do programming. How people do programming? Okay? Organize data in a tabular way. Okay? Put in the table, arrange in the table, organize the way, tabular. Okay? So that's the programming. Original meaning of the programming. So dynamic programming, your data is dynamic. Okay? The data comes in, okay? One after another, dynamic data. Okay? Yeah. So, but you arrange in a table. Okay? That's the dynamic programming. Okay? All right. So now we need to use that original meaning to organize our data. Look at a simple example. Yeah. But a little harder than our first example. First one too easy. We do not need to do any work. We can get an answer immediately. So, now we really need to do some work. So I make an example a little harder. This time we have 4 denominations, 1, 3, 5, 7. But our goal, the number of cents, 23. It's a much larger number, although it's still not too big. We can handle, but we need to do that table way, tabular data, organize, So here you can see, to solve a computing problem, how important it is to organize your data. If your data is very messy, very, very messy, then it is hard to solve the problem. If you can make your data well organized, then it will be a lot easier to solve the problem. So here, let's see how this idea works. Let's work. Let's do our work. I create this table. Tabular, this is my table. Okay? Or another word people call dictionary. This is my dictionary. Okay? The reason probably why some people like this dictionary name, because the basic property, basic feature of a dictionary, people can look up words in a dictionary. Here, we need to do this lookup operation. We need to find the values we already computed in this table. So it's a dictionary. We use it as a dictionary. Okay, all right. At the beginning, let's put some relatively easy number first. Okay, yeah. All right. Because think about if we only use one coin. Think about think about this. If n equals the face value of each coin denomination, then we need one coin, right? 1, 3, 5, 7. That's trivial. It's a trivial solution. All right. That's first. The second. Okay. Second. Yeah. Then, all right. Look at 2. 2, definitely you cannot consider coin 3, right? Coin 3. Coin with denomination 3, with face value 3. Okay. So you can only use face value 1 coin. Okay, so you need a 2. 4, you can use 1, 3, 1 plus 3, so you need a 2. Okay, 6, 1 plus 5, you need a 2. Okay, yeah. For the relatively small one, we can do it easily. But when n number is larger, it is hard to use the observation method. Observation. So we try to use our mind to, figure it out. That will become harder and harder. So we don't do it in that way. Now let's use the recurrence relation to do it. Okay, 1 by 1. Yeah. So let me do that work, 1 by 1. Yeah. So that's a lot of work. All right, let's do it. The first one, S8, based on our formula, 1 plus the minimum, the 8 value minus each denomination, okay? Minus 1 S7, minus 3 S5, minus 5 S3, minus 7 S1, okay? But each of them, 1, 1, 1, 1. So minimum of these number 1, 1 plus 1, 2, okay? So we get S8 equals 2. Okay? Things like this. S9, right? So 1 plus minimum, 9 minus 1, 9 minus 3, 9 minus 5, 9 minus 7. Okay? But those numbers, all the minimum 2, 1 plus 2, 3. Okay? So we do it like that. Okay? We can keep doing like that. Here, I think I can go fast, right? 10, we do this. The minimum of these numbers, yeah, so 1, right? Yeah, we can find a 1, so we use that 1, so 2. Okay, yeah. S11, the minimum number of that 2, right? So we get 3. 12, the minimum number of that 1, so we get 2. 13, the minimum of that 2, right? So we get 3. 14, the minimum of that 1, so we get 2. 15, minimum of that 2, so we get 3. All right, now we need to, do the remaining numbers. Yeah. S16, minimum of that, 11, 9, so which one's smaller? 13, yeah, all 3, so we have to use that 3, so we get 4. 17, those numbers are 2, yeah, we can get 2, so 3, yeah. 18, 11, yeah, 3, yeah, so 4. 19, yeah, 12, yeah, 2, we have 2, yeah, so 3. 20, yeah, 23, yeah, 4, yeah. 21, minimum, right, yeah, 2, yeah, we have 2, so 3. 22, yeah, we can only find minimum 3, right, so 4. Yeah. Last one, the final answer, 23, 22, 4, yeah. So all these number 4, I see, yeah. We cannot get smaller than that. So the final answer is 5. Okay. Although for us, it's tedious work, right? So if we do on our scratch paper, tedious work, but for computer, for your program, that's simple, right? So you write a for loop, so you can easily calculate. Yeah. Here you can see when you write a for loop, implement these steps, you manage your data in a well-organized way. That's the reason you can solve this problem. If you can manage your data in a well-organized way, you can solve your problem in a nice way. Okay, so that's the conclusion of this problem. Okay. All right, so we finished this part, 8.1.